Good morning, good afternoon to everyone watching this presentation. My name is Daiane Conceicao and I will present the work entitled An Investigation in the Impact of Tower Height Variation on Transmission Lines Backflashover Rate, Considering Different Probability Distribution. This work was developed by me, Daiane Conceicao, and by my supervisors, Ivan José da Silva Lopes from UFMG and Rafael Alípio from the Electromagnetic Transient Laboratory of Cefet-MG. The presentation consists of 5 parts: introduction, modeling guidelines, methodology, results and discussion, summary and conclusions. Due to their long extensions, transmission lines, in general, have a high number of structures and can cross regions with a vast range of topographic features, soil resistivity, and ground flash density. Different tower geometries are used along the line with different heights depending on the case. Due to all the specificities mentioned above, sections of the line that eventually have higher structures can be critical, in view of the greater exposure to the lightning incidence. In general, the approach used to assess the line performance considers the length of the line as a whole. The identification of critical stretches can allow the implementation of measures to improve the performance of the line efficiently, implementing the measures in the specific stretches and not in the transmission line as a whole. Lightning performance estimation is a complex process that involves many uncertainties. As a result, simplifications are commonly adopted. However, adoption of some simplifications must be carefully evaluated, as they can lead to different results. A commonly adopted simplification, in order to simplify the calculation, is to consider a representative average height for the towers along the line. The goal of this paper is to evaluate the impact of the high variation of a given tower geometry on the line outage rate, considering different distributions of peak lightning current value. Since lightning parameters vary from region to region, 3 distributions are considered in order to obtain a more realistic analysis of the influence of tower height on the line performance. The current waveforms of figure have been adopted in the simulations. These curves closely reproduces the mean-median parameters of negative downward lightning first-stroke currents measured at Monte San Salvatore and Morro do Cachimbo station. These waveforms are modeled as the sum of Heidler's functions. The statistical behavior of the peak value of the lightning current is described using the log normal probability density function. Integrating equation 1, the respective cumulative probability functions associated with Monte San Salvatore and Morro do Cachimbo station are obtained. Equation 2 corresponds to the expression recommended by IEEE to calculate the probability of occurrence of the critical current and the estimation of the backflashover rate. The transmission line tower was modeled as a lossless single-phase line. The surge impedance of this line is calculated with the revised Jordan's formula, which extended to take into account vertical multi-conductor systems. Figure shows geometry details of one tower geometry used in simulations. The tower was divided into 5 sections, each one represented by 4 parallel conductors. This was made to consider the variation of the tower cross-section with position. Figure shows the geometry details of the transmission line Gaia tower. The central mast was divided into 2 sections of 4 parallel conductors, both having the same surge impedance, since the distance between the parallel metallic conductors is basically constant through mast body. Each guide wire was represented as a single vertical conductor whose surge impedance was calculated. The equivalent impedance of the guide wires is placed in parallel with the mass surge impedance at their connection point, as indicated in the tower model. The tower height variation was performed by varying the base height according to the base lengths and extensions available for the presented geometry. For each value of x and respective total height of the structure, the surge impedance of each segment of the suspension and the Gaia tower were calculated. The grounding system is represented here by the impulse impedance. Through the impulse impedance, it is possible to characterize the impulsive behavior of the grounding in a simplified way. This representation leads to results very close to those obtained using the harmonic impedance, which is the most rigorous way of representing the behavior of the ground system. All the results were obtained through simulations carried out in the ATP. The lightning current is injected at the top of a central tower in order to consider the effect of the reflections in adjacent towers and the effect of the propagation of overvoltages along the line conductors. A pair of towers adjacent to the stricken tower and identical to it was included in the simulations. To carry out the simulations, a line with 220 structures was considered. The impulse impedance values were ordered in ascending order and divided into 10 sets, each comprising 22 structures. Mean values were calculated for each set and the result is shown in figure. These then values correspond to their impedance distribution used in all the simulations carried out through the paper. The backflashover rate was calculated using the expression, where Ng is the ground flash density. P is the probability of lightning current being greater than the critical current. 0.6 is a factor used to disregard the effect of strokes within the span. And W is the attractive width of the line and is given by the total value backflashover rate is given by the expression, where N is the total number of towers of the entire line and N corresponds to the number of towers per section and K the number of sections that the transmission line was divided. Three lightning current peak values distributions are used in the simulations. From table, it is possible to observe that considering self-supporting tower and the distributions presented as the height of the tower increases, the outage rates due to backflashover of the line increases. This behavior was already expected since as the height increases, the area of exposure the line also increases. Considering the distribution recommended by IEEE and the distribution associated with Morro do Cachimbo station, it is possible to observe a difference between the highest and the lowest backflashover rate values of approximately 75% and 8% respectively. This value is even higher for the distribution proposed by Anderson and Eriksson, for which this difference reaches 118%. The same behavior is observed with Gaia Tower. As the height of the tower increases, the outage rates due to backflashover of the line increases. Considering the distributions of IEEE and Morro do Cachimbo station, it is possible to observe a difference between the highest and lowest backflashover rate values of approximately 55% and 67% respectively. For the distribution proposed by Anderson and Eriksson, this difference reaches 90%. It is important to note that the probability distribution used directly impacts the variation of backflashover rate as a function of tower height. For a better estimation of the lightning performance of a transmission line, it is very important to choose a probability distribution that is as representative as possible of the line activity characteristics of the region where the line is installed. In this work, the effect of the variation of the highest of the tower geometries along the transmission line route on the lightning performance were investigated, assuming a typical 230 kV line. Three different probability distributions were considered for two tower geometries. The differences obtained considering the three evaluated distributions are high for the two tower geometries evaluated in simulations. In view of this impact on the line performance, it is important to carefully choose the distribution to consider. The differences obtained in this study are very relevant in view of the constructive characteristics of the line. Transmission lines, due to their long extension, typically have different tower geometries with different heights along the route. In this context, there may be sections presenting higher backflashover rates due to the presence of structure with higher towers, higher ground flash density, etc. These sections are considered critical and can strongly affect the overall performance of the line. An eventual action to mitigate the cause of outages and improve the transmission line performance, these sections must be prioritized for the application of protection. For more details on the subject, the authors recommend reading previous works developed by them on the transmission line performance. The topic continues to be explored and soon more works on the subject will be published. If you have any questions, please do not hesitate to contact me. Thank you for your attention.